linear programming. And it is directly, it's a direct extension from what we've been talking about in the previous section. So we're going to do exactly what we did in the previous section and add a little bit more to it. And what we're adding is we're going to add in this process. Well, for linear programming, we're going to add in this process of maximizing or minimizing some function that they give us. So on top of graphing the inequalities, as we've been doing before, we are then going to use that graph to maximize a function. And so today we're going to talk about just regular examples, and in the next class we'll look at more applications of this. So let's go ahead and look at example 1 here. Yes?
Is the homework on this too, or is it just the last section?
So is the homework for the one that's due tomorrow?
Yeah.
That's for everything before this.
Okay.
The homework for this, I'll end up assigning this sometime next week. So linear programming here. Let's go ahead and see some of this stuff in action for example 1. So notice they tell us they want us to maximize this equation here, and then they give us a system of inequalities. Now, we're only going to focus on the system of inequalities for now. We're going to ignore that maximize whatever. We're going to completely ignore that. Now, the downside of this section, which for some reason, they do not let you graph anything on my math lab. You have to generate the graph on your own from scratch. What I have in my notes is just a template. And as you might foreshadow a little bit later, I do have problems where I just have blank spaces, or I just have a complete blank space and I will be drawing everything in. But to start off, I wanted to show you the process, sort of give you a template of what you should do. And your graph doesn't have to be perfect, but it does have to exhibit a few characteristics. Now, so again, I just want to give that disclaimer. These graphs, these tables are not given to you. All it will say is figure this out, and it will ask you to actually solve these two. It will not, there's no in between for this. Everything I have is just for your convenience. So with that being said, let's go ahead and graph the inequalities. Now, these two down here, you might recognize those. Those are the non-negative restrictions, which you should get used to in this section, because in this section, this is a lot more application-based. So since we're dealing with applied concepts, they generally take on non-negative values. But all that means is, okay, so we're going to have lines on the axes. We can go ahead and do that. All right, so that takes care of the non-negative restrictions. Okay. So now let's look at the other inequality here. The x plus 2y is less than or equal to 12. Let's go ahead and graph that. We're going to graph it the same way we did before. Find the x and the y-intercepts, which, again, hopefully you can derive the math for yourself. X is 12 and y is 6. For the x-intercept, you set y equal to 0. That one would just be x is 12. Y-intercept, you set x is equal to 0. Divide both sides by 2, and y is 6. But we have that, so we can graph 12 here. And for my template, or 6. Goes by increments of 2, so I'll put that there. We ask ourselves, do we get a solid or a dotted line? We get a solid line. Because our inequality symbol has an equal to part, just like before. So we can go ahead and connect the dots here. And since there's no other lines to graph, we can just go ahead and start shading. And by that, we're testing 0, 0. So this tells us, do we shade above or below the corresponding line? Remember, that means we plug in 0 for x and 0 for y in our corresponding inequality. We get that 0 is less than or equal to 12, and we get a true statement from that. Before, we got a false statement, and we had to shade above the line because of it. Here we get a true statement, so we shade below the line. Well, I guess not L1. I don't really have any labels here. It's just the line. So we're shading this little region here. We're shading this region right here. And there's no paint bucket tool that I have to poorly illustrate because this is not a graph that will be resembled in my math lab. Again, this is a graph you will have to draw on your own. Now, your graph needs to be only as perfect as the information you need to derive from it. You need to make sure this graph is drawn well enough to where you can determine the corner points. Now, you need the corner points. That's the only reason why we care about drawing this graph. Now, the corner points, we discussed it fairly briefly in the previous section. The corner points are the vertices that surround our shaded region. The vertices are any places where 2 or more lines intersect. So that we actually have 3 vertices here, and 2 of them are already dotted in red. I'll add the additional one down here, because the origin is technically a vertice here, because the 2 non-negative restrictions, I guess relative this way to you all, they intersect at the origin. So we have 3 corner points here. That's a corner point, that's a corner point, that's a corner point. These are the vertices that surround our shaded region. This is why, this is to the extent of how good your graph is drawn. You need to draw a graph good enough so that way you can see what the vertices, at least what they refer to. Now the origin, that one should be pretty simple. That one's 0, 0. That's always the origin. Let's go up from the origin to the one on the y-axis. Now that looks like it's the y-intercept for that line we drew. What was the y-intercept for the line we drew? It was 6. So the ordered pair is 0, 6. And then let's move down to the x-axis. So the one near that 12 there, that's the X-intercept, which was 12. So again, your graph needs to be good enough for you to at least identify this stuff. It doesn't have to be perfect, but you need to at least determine, okay, this looks like the y-intercept. What was the y-intercept? And you actually found the y-intercept in more detail, and the x-intercept as well. So that's all the information we can derive from the graph. The only reason you draw the graph is so you can figure out those corner points. Now, this brings us down to part B. We're going to take all those corner points we found and put them into a table. Now, again, this table will not be given to you in my math lab. This is a table, I'm giving you the template for now, and then on problems on your own, you will need to draw this table for yourself. Notice I put all the corner points there. There's no real order to them. I just listed them there. So again, this is a table you need to construct on your own, but you can gladly use my notes as a template. They also have the objective function, and then they have this random equation right here. P is equal to 20x plus 80y. I don't remember seeing that in any of the inequalities. However, it was stated at the very beginning of the problem. That's where it comes from. That's not just an arbitrary choice. Now we're bringing in, so this is the new information. Everything we've done prior to this was stuff from the previous section. Now we're throwing in this maximize equation stuff. And we're starting off with just the equation, the 20x plus 80y. That's why I wrote it down here. And what we do with this, we found 3 points, and we're plugging each one of those points, because each one gives us an x and a y, into the objective function. So 20 times, so this point is 0, 0, so we're plugging in 0 for x and 0 for y, and figuring out whatever the output is. Whatever that output is, that's what we put in our second column. And so the next one, this one says that x is 0 and y is 6 for that row. And that's 480. And then finally, 12 for x, 0 for y. We get 240. So those are the numbers that go into the second column. For each ordered pair, we're given a different set of x and y that we plug in for, well, x and y. So normally the graph is the difficult part, but once you figure out the corner points, that's where, so the extension of this is much easier, but graphing everything on your own, it's honestly it's a pain. So, but once you find the values for the objective function, well, they first want us to determine, since the region is, and this is going to be either bounded or unbounded. Now, our shaded region does not just shade off continuously in any direction. It's trapped by line segments all around. So this is a bounded region. And the reason why they even care, they want us to care about that, if you have an unbounded region, you do not have a maximum. And they wanted us to find the maximum. If you have an unbounded region, you cannot find the maximum. That's because if you keep growing and growing and growing without bound, then there's no max, because it never stops growing. But it is bounded, which means we do have a maximum. The maximum is the largest value of your second column. We got 0, or we found 0, 480, 240. The maximum is the largest number. It's 480, the largest number. Part D says, well, what was the ordered pair that gave you that largest number? So all we have to do is look over here. What was the ordered pair that contributed towards that? 0, 6. So when you see this problem in your homework, all you will see is the statement and parts C and D. You will have to do A and B on your own paper. But don't be too shocked to, that's why I want to warn everybody about this before you do the homework for this section. And the homework for this section is going to be due sometime, let's see, today's Thursday. We'll probably finish this on Tuesday. It'll be due Wednesday at the earliest. At the earliest. I don't know what day I'm going to assign it yet, but when you do start looking at this homework, then yeah, it's only going to skip down or only show C and D, and you have to do A and B on your own. But this is linear programming. Does anyone have any questions before we move on to the next example? Now let's go to example 2. which is almost the same exact problem, but we added an additional inequality. So they gave us another equation to maximize, which we're going to ignore for now. And mainly we're going to focus on these inequalities down here and graph. We're going to graph them. Again, this is the graph I have in the subsequent table. Those are just templates. You will have to construct those on your own. But let's go ahead and take care of the non-negative restrictions first. Again, just solid lines on the X and Y axes. Now we have two non-trivial inequalities. Now I'm going to give them a little bit of labeling. L1 and L2. I'll start off with L1. The X-intercept and the Y-intercept. And hopefully you can quickly determine that X is 10, Y is 20. These go by increments of, I believe, 2, 4, 6, 8, 10, and 20 for Y. We ask ourselves, do we get a solid or a dotted line? Looks like we get a solid line because the corresponding inequality has an equal to part. And so we can just draw a solid line connecting these 2 points. Try one more time. There we go. All right. So after that, again, we have another line that we have to look at. So we're not going to shade quite yet until all the lines are drawn. So the second line is X plus 2Y is less than or equal to 16. And so from here, we can go ahead and first determine the X and Y intercepts. Looks like X will be 16 and Y will be 8. That's 10, 12, 14, 16. Y is 8, 2, 4, 6, 8. And then part 2, is the line solid or dotted? We get a solid line. So we can go ahead and draw that line. So now that all of the lines are drawn, we can go ahead and try to figure out, well, where do we shade? Because in essence, we have 1, 2, 3, 4 different regions. We need to figure out which one of those 4 do we shade. Let's start with the red line, the first line. And again, on your paper, I definitely recommend putting an L1 next to the first line you drew, which my paper was red, and L2 next to the second line. Because if you don't have colors, it's going to, it might be a challenge to remember which one is which. So let's look at the first line. We're going to test 0, 0, which means plugging in 0 for X and 0 for Y of the corresponding inequality. And we get what seems to be a true statement. Get a true statement. which means we shade above the red line, or below, I'm sorry. We shade below the red line. Shade below L1, because we obtained a true statement. That rules out 4 and 1 here, because those are above the red line. So we're down to regions 2 and 3. To narrow it down to the final region, we need to test 0, 0. So we plug in 0 for X, 0 for Y, and we get a true statement yet again. So this tells us we shade below L2, the second line. So that's the line we tested, which rules out region 3, because that region 3 is above the blue line, or above the second line. And so that leaves this bottom left region here, which we can go ahead and shade. That tells us the region that we need to shade, and ultimately tells us, well, what corner points do we need to consider? Because there's technically a bunch of corner points, but we care about the ones that surround our shaded region. And we actually have 4 corner points here. The origin is 1. That one's the easy one. The 2 that are less easy, maybe, are the one that's near the L2, the L2 label right up here. The one down here at the end of L1. And actually the point of intersection between the 2 lines. Because remember, a corner point is any time that 2 lines intersect. Now that corner point, that's the intersection between the first line and the second line. So we have 4 corner points, and I illustrated all of those using black just to really emphasize them. Now, let's start with, I'll start with the one right here. Now that point, see, now this is where the approximation of the graph you draw on your end, it doesn't have to be perfect, because you might see that point and think, well, I don't have grid lines or anything. What point does that correspond to? If anything, that point is right next to the L2 line, and this point lies on the y-axis. So in other words, this point is the y-intercept of your second line. Wait a minute, we found the y-intercept of the second line. It's 8. So that would tell you that this is 0, 8. And additionally, let's move down to the x-axis and look at this point. Again, you might see that point just drawn on your paper and think, I don't know what point this is, or I don't remember. Well, if you trace up that line, it goes all the way up to L1. So this is on the x-axis for the L1 line. Or in other words, this is the X-intercept for the first line. The X-intercept for the first line, we found that. It was 10. So there's 3 of the 4 corner points right there. Now finally, we need to figure out the point of intersection between the 2 lines. Point of intersection between L1 and L2. Now the point of intersection, again, if you're drawing this on your end, you might not be able to, you might not have grid lines available to you So that way you can figure out what that point of intersection actually is. So if you can't use solving the system by graphing, then what's the most efficient way to determine where two lines intersect at? The most efficient way is by using augmented matrices. I recommend using augmented matrices here. So we're trying to figure out where these two lines intersect at. Here's the two lines right here. We need to turn those two lines into an augmented matrix. It's 2, 1, 1, 2, 20, and 16. And we need to use, for the augmented matrix section, we've dedicated a whole section to this. This is where we use the RREF command, which normally gives the first two columns as this, and then they give us an additional column, which we're going to go ahead and figure out. Now again, if you need a refresher on how to do this, I would recommend going back to the augmented matrix section. Again, all the calculator tutorials are in the notes. This is a 2 by 3 matrix. We can go ahead and put all of the entries in. So remember, the RREF command is under math. Go down enough and you see RREF. Not just one R, you need the one with 2 R's. And we need to take that for the matrix A, which gives us the final column of 8 and 4. And that tells us the point of intersection, actually. That final column tells us that the point of intersection is 8, 4. Okay, so we have 4 corner points here. And now we can add all of those corner points to our table, our subsequent table down here. 0, 0, 0, 8, 8, 4, and 10, 0. Again, the order doesn't matter. I'm just placing them there. So if you need to look at the top part, I'll leave it here for a few seconds. You still need to jot down the matrix stuff. So now we're down here to the table in part B, and notice how the objective function is 7x plus 7y. And this is consistent with the objective function that they gave us at the very beginning of the problem. So that's not just an arbitrary placement. You would need to remember to place this objective function here. And so this tells us exactly what to plug these ordered pairs into. 7 times 0 plus 7 times 0. 7 times 0 plus 7 times 8. 7 times 8 plus 7 times 4. 7 times 10 plus 7 times 0. So that one's 56, that one's 70, and this one's 84. Should be 84. So once you find the corner points, the rest of the problem works out pretty nicely. The main hassle of this section is correctly determining the corner points. Now it goes on to ask, well, it first wants us to determine if the region is bounded or not. And the region is yet again bounded. because the region is surrounded by line segments on all sides. The region doesn't just go on indefinitely in some direction. And since the region is bounded, this means that we do in fact have a maximum. And so from here, the maximum value itself is, well, the largest number in our table. It's the 84. It's larger than the other three. So the largest value is 84. And the ordered pair that gave us 84 was 8, 4. That concludes this example. Does anyone have any questions before we move on to example 3? If not, we'll move on to the next example, which looks very similar to the previous example, but yet again, we add another inequality. So now we have 3 non-trivial inequalities. But the same setup nonetheless. In fact, let me go ahead and take care of the non-negative restrictions. So from there, so from here we need to graph the 3 inequalities here. The 3 inequalities. Again, I'll call these L1, L2, and now L3. So this will start off fairly similar to the problem we did at the end of the previous section. That one had 3 non-trivial inequalities. This one has 3 non-trivial inequalities. So let's start off with the first one. 2x plus y is less than or equal to 10. The x and the y-intercept, x is 5 and y is 10. And these seem to go by increments of 1, so 1, 2, 3, 4, 5. And then 11, 10. Just to save a little bit of space, we can already foreshadow that all of these lines are going to be solid lines. We have nothing but equal to's for our inequalities, so we're going to have all solid lines. I'm just going to go ahead and make that as a statement, save a little bit of space. So I'll go ahead and connect these 2 dots. Let's do the next line. X plus y is less than or equal to 7. Yet again, it's a solid line, as we already foreshadowed. Look at the x-intercept and the y-intercept, which both seem to be 7. And for the third line, actually, let me go ahead and plot the second line. 7, 5, 6, 7, 8, 7. And again, I do recommend each time you draw a line, putting L1, L2 next to the corresponding lines, as I have here. And let's go ahead and move on to L3. X plus 2y is less than or equal to 12, which is also a solid line, as we, again, already foreshadowed. The x-intercept and the y-intercept we can quickly determine. X-intercept is 12 and the y-intercept is 6. There's 12 and there is 6. So now we have all 3 of the lines plotted, and we need to figure out where do we shade. Now that we have all the lines plotted, we figured out that all the lines are in fact solid. Let's go ahead and test 0, 0 for each one of these lines. So for the first one, we get that 0 is less than or equal to 10 after you plug in 0 for x and 0 for y. And we get a true statement, which means shade under L1. So we're not shading up here. We're not shading any of those 3 regions that I put the X's at, because all of those regions correspond to being above that line. Oh yeah, let me put L3. There we go. All right, let's move on to the second line. Test 0, 0. We will end up getting that 0 is 0 is less than or equal to 7, which is true. So we shade under L2. So that leaves this region here, and this tiny region in between the blue and purple line up here. So finally, we test the third line to see which one it actually ends up being. And what we end up getting is 0 is less than or equal to 12, which is true. So we get another true statement, which means we shade under that corresponding line, L3. So we're shading under the third line, or in other words, the purple line. And so from here, that tells us exactly what region to look at. It's bottom left region, which seems to be the trend so far. We'll see throughout the section, it's not always this bottom left region, but it seems to show up, well, for every example thus far. So that bottom left region is what we are looking at, which means we only care about the corner points that correspond to that shaded region. We actually have 5 corner points here. We have 5 corner points. And your graph needs to be good enough to where you could see where these corner points are at. One of them is the origin, yet again. The ones that are a little bit more challenging to find, one is the point next to the L3 label that I have here. So let's go ahead and figure out that one. So that point, that's on the y-axis, and it's next to L3. So it's the Y-intercept of L3. The Y-intercept of L3 we found over here. Y is 6. That's 0, 6. So there's another corner point. I'll skip down to this one right here. That is also a corner point. And so if we trace up that line, this is the L1 line. So it's when L1 hits the x-axis. So it's the x-intercept of the first line, which seems to be 5. That's 5, 0. So now we have 3 corner points here. there's actually two more corner points. This is a corner point right here, and this is a corner point right here. Those are both corner points. They're both intersections between two lines. And the first one is the point of intersection, so POI, point of intersection, between, it seems to be between L2 and L3, because that's where the second and the third line intersect at. And then the other point is the point of intersection between, that seems to be between L1 and L2. Now, how do you find the point of intersection between two lines? You have to use matrices. So I'm going to do both of these matrices. That does mean two sets of matrices. I'll do the first one, the point of intersection for L2 and L3. I'll do that one on the left side here. L2 and L3 are these two lines. And so the augmented matrix, 1, 1, 7 for the first row, 1, 2, 12 for the second. It normally gives us a template that looks like this, with a final column that we need to now figure out. And so from here, again, once you program the matrix into the calculator, you need to use the RREF command, and you'll find matrix A. And we get for that second column, or that third column rather, 2 and 5, which tells us one of the corner points. 2 and 5 tells us that the point of intersection that we want to know is 2, 5. So that's the fourth corner point. And the second corner point seems to be the point of intersection for L1 and L2. Now that matrix is going to look like L1 is the top one and L2 is the second one. So we need to make a matrix between those two. 2, 1, 10, 1, 1, 7. So from here, that means another matrix that we need to compute in the calculator. Two, 1, 10, 1, 1, 7. Once you do the RREF command once more, you will get 3 and 4. So that point of intersection is 3, 4. And so from here we have 1, 2, 3, 4, 5 points of intersection. And so for anyone who might still be writing the matrix stuff, I'll give you a few more seconds to write down that before I scroll down. Let's go ahead and move down to actually placing the corner points into our table. Again, it doesn't matter what order you do it in. We found 5 corner points, and I'm putting them into the first column of our table. And again, the top of the second column, it says objective function followed by 40x plus 50y. Again, this was given to us in the very beginning of the problem, 40x plus 50y. So that's not just coming from nowhere, that's coming from the statement of the problem. But now we know exactly what to plug our ordered pairs into. 40 times 0 plus 50 times 0. 40 times 0 plus 50 times 6. 40 times 2 plus 50 times 5. 40 times 3 plus 50 times 4. 40 times 5 plus 50 times 0. First one's obviously 0. Next one is 300. Next one is let's see, that's 80 plus 250, that's 330. Oops, not that, 330. Next one is 120 plus 12, that's 320. And the final one, 40 times 5 is 200. So now we yet again ask, is our region bounded or unbounded? It's definitely bounded because it's again surrounded on all sides by line segments, which means a maximum does exist, and the maximum is simply the largest number in our table, just 330. That's the largest number. Ordered pair for that number seems to be 2, 5. And that concludes this example. So once you find the corner points, the problem moves a lot more quickly. It's very tedious, which is why I am posting the recorded lectures for this recorded lecture here. Very dense stuff. Does anyone have any questions before we look at the next example? Again, we're not going to be able to finish this section today, but hopefully it'll even help with the linear inequality homework that's due tomorrow. Is it due tomorrow? I believe it is due tomorrow. I already forgot. Okay, example 4 is very similar. It's still 3 non-trivial equations. The only difference between this problem and the previous example is that instead of just maximize, they also throw in minimize. And minimize doesn't really change much of anything, luckily. So basically, maximize is you find the largest value in the table. Minimize, you find the smallest value in the table. That's the only difference. But the process is the same. So let's go ahead and start off with the non-negative restrictions. So that takes care of the non-negative restrictions. And so I'll go ahead and label the 3 inequalities here, as I've done before. Let's go ahead and start off with the first line. 2x plus y is greater than or equal to 56. Which, as we did before, we could see that all of these are going to be solid lines because all of their inequalities have equal to parts, as I've been saying before. So we're not really going to worry about that too much. So let's go ahead and figure out the X-intercept and the Y-intercept for the first line. The X-intercept seems to be 28. We divide by 2. And the Y-intercept is 56 because there's nothing to divide next to the Y. These increments, if you have the notes printed out, they go by increments of 5, I believe. So 5, 10, 15, 20, 25, 30. So 28 would be in between those. And 56, 60, 55. So 56 would be right above that tick marker. We already said it's a solid line, so let me go ahead and connect these two dots. Okay. L2 is x plus y is greater than or equal to 40. You can go ahead and figure out the x and y intercepts for this one. And also the line is, again, solid, as we already foreshadowed. Looks like x and y both end up being 40. That's 30, 35, 40. 5, 10, 15, 20, 25, 30, 35, 40. And so we can connect those two dots. And let's do this for the next line. X plus 2y is greater than or equal to 48. The x-intercept and the y-intercept. X-intercept 48 and the y-intercept is 24. After you do the math for those. 40, 45, 48 would be right here, looks like. And 24, 5, 10, 15, 20, 24. So really from this part to conclude with the graphing of this, we need to shade a particular region. Now there are 1, 2, 3, 4, 5, 6, 7 regions going on here. We need to figure out which one we shade. So we need to test this for every single line, just like we did last time in class, and even, I believe, the time before. So we test 0, 0. And remember, you plug in 0 for x, 0 for y. Get that 0 is greater than or equal to 56, which is false. So for the first one, we shade above L1, because that's the line we're testing, the first line. So we don't shade below L1. Any region that's below L1, which is those three, we don't shade any of those. What about L2? Let's go ahead and test 0, 0 for the second line. And when you plug in 0 for x, 0 for y, you get that 0 is greater than or equal to 40, which is a false statement. So we would, once again, shade above L2. So we don't shade below L2, which would get rid of that region and that region that I just X'd out. So now we're left with two regions. We're left with 2 remaining regions. One up here and one down here. So let's figure out which one is which. For the last line, we'll test 0, 0 yet again. So this is 0 is greater than or equal to 48, which is a false statement. Once more, we shade, as a result, we shade above L3. Which means we really do exit out that region down there, and we keep this outer region up here. This is the region we shade. So we can shade this region out here. So all of this. And so with this shaded region, we have what seems to be 4 corner points here. Remember, corner points are any places where two or more lines intersect adjacent to the shaded region. So we actually have 4 of these. This one near L1, and I'll fill these in black to really emphasize them. The point of intersection here, this point of intersection here, and then this, it seems to be X-Intercept, yes.
How do you know what order to put them in? Because on my math lab, it does something different.
It does, I mean, that's kind of vague. It does something.
You just have to do the
But sometimes you tell me that it's wrong when I don't put it in a certain order.
So I'm kind of not understanding what you're asking, to be honest.
Like how you went down the road, like if I went down, it may say I had to go the reverse way, or the 2 middle points might go first and then the 2 outside points.
She's talking about the corner points. In my math lab, when it asks for them, is sometimes if you don't put in the right order, it says it's wrong.
Really?
Mm-hmm.
Can I look at it after class? Is that fine?
Yeah.
It might be something, as far as, so it will mark it wrong if you don't put, so for the first corner point here, the Y-intercept, this is the Y-intercept of L1, which is 56, which you would have to put 0 and 56. If you switch 56 and 0, that's one thing that comes to mind. But if it's
like I'll write them out correctly, the numbers in the X and Y intercept or whatever, but the order of the corner points, they tell me is wrong if I don't have it in the order that they have.
It's interesting. Let's look at it after class, if that's all right. Okay. So remind me after class. We'll look at that. That's no problem. So 0 and 56, that's the Y-intercept of the first line, which we determined was 56. Another one we can go ahead and quickly figure out is down here, the X-intercept of what seems to be L3. X-intercept of L3 seems to be 48. And then that leaves us with these 2 points, these 2 points of intersection. So the points of intersection, well, because these are, in fact, points of intersection, we need to use matrices. This is the point of intersection for, it seems to be L1 and L2, because we can see the first line and the second line cross. And then the point of intersection for this one seems to be L2 and L3, which means that's 2 separate matrices that we need to construct, because matrices are the most efficient way of determining where 2 lines intersect. So let's do L1 and L2 on the up here on the left. Now, L1 and L2 are these 2 lines right here. And as an augmented matrix, we have exactly this, just taking the numbers and bringing them straight to a matrix. And so we can go ahead and apply the RREF command to figure out what the point of intersection is. So this is a 2x3 matrix. And from here, we can go ahead and determine the RREF for that matrix. Which tells us that the point of intersection is in fact 16 and 24. So that column tells us precisely what one of these corner points is. So 16, 24. So far we have 3 of the 4 corner points now. And so for the last one, this is the point of intersection between L2 and L3. So I'm going to erase that little box that I had around L1 and L2 because we have two new lines that are being intersected with one another, L2 and L3. 1, 1, 40, 1, 2, 48. We simply take the coefficients and put them straight to a matrix. And it's the same idea. We throw it straight up the calculator and see what we obtain. And we get 32 and 8. That 32 and 8 is what gives us the final point of intersection. So we have 4 points of intersection now. Well, 4 corner points ultimately. And with these 4 points of intersection, we can go ahead and, well, these 4 corner points rather, we can go ahead and put them into our table. Now notice with this table, they also have this objective function listed here on atop the second column. That objective function doesn't come from thin air. It comes from the statement of the problem in the very beginning. So again, that's why the 40x plus 30y makes a recurring appearance here. It's some useful information that we haven't utilized yet. This is precisely where we utilize it. But now that we know the ordered pairs, we know exactly how to plug these ordered pairs in. Plug 16 and 32 and 48. The other one, 24, 8, and 0. And so these are a bunch of computations we need to quickly determine. 30 times 56, 40 times 16, plus 30 times 24, 40 times 32, plus 30 times 8, 40 times 38, plus, well, really, plus nothing. So here's our 4 values. So a bunch of tedious computations, but this allows us to determine the values of the objective function for each ordered pair. Now it goes on to say, since the region, so we're moving on to part C, since the region is either bounded or unbounded. So with this, we can check our shaded region. Our shaded region is unbounded here. Unbounded, it goes up without any line segments cutting it off, goes to the right without any line segments cutting it off. So this is an unbounded region. Yes?
If any of them were true, like they're all false, so it's unbounded, but if one was true and the others were false, it would still be considered bounded.
Yes, because of where the new shading, anytime, so with the non-negative restrictions as well, which are always in this section at play, anytime you get a true statement, you're under a line. And as soon as you're under a line, you're bounded by that line. So that's one way to kind of substantiate what you said. So this unbounded characteristic In fact, this is going to be true for C and E. So it's unbounded no matter what. Now, the repercussions of unbounded, it doesn't affect minimum at all. Minimum is not affected here. The minimum value, when we have to find the minimum, but it's the exact same thing as maximum, except we find the smallest value. Smallest value here seems to be 1,360. And for the next part, just like we did in the last section, this one's the ordered pair. That corresponds to that minimum value. Now, as far as maximum goes, and I stated this in the last class, if the region is unbounded, the maximum does not exist. This is undefined. Undefined. We could find a maximum. I mean, the largest value is 1,920, but the context is that we have an unbounded region. And the repercussion of that is that we have a region that grows and grows and grows without bound, which means that you cannot have a maximum because the area grows infinitely. There's no max. The context that sort of allows us to say undefined. Does anyone have any questions before we proceed to example 5? If not, these following 3 problems are going to be word problem oriented. So, and I also have taken away the templates from before. So now we don't have a graph at all, a template of a graph. Now we don't have a table. And so we need to figure out everything and derive everything from scratch, which would be more characteristic of, so this would be more characteristic of, say, homework problem. You're given absolutely nothing. So, so this example, you might recognize the context. Yet again, there's a word in here that I can't pronounce, so I'm not going to. There's 2 types of skis, though, and they gave us a table. They very generously gave us a table. But they didn't give us, well, if we look back at the previous examples, normally they give us maximize, objective function, linear inequalities. So we can't really do anything until we get maximize, objective function, inequalities. So guess what we have to do? We have to find the objective function, whether we maximize or minimize, and get some linear inequalities. And that's how this table is going to help us. And additionally, they say something about, in part A, profit is 40, and the profit is 60, and then they want to get a maximum out of that. So this is a bunch of numbers they're throwing our way. Now, if anything, if they're trying to maximize the profit, in fact, before I even write that, now your thought process should still follow the thought process of the previous examples. The first thing we need to do, though, unlike the other problems, is we need to determine the objective function and constraints, as they're called. Constraints just means what are the inequalities. So the objective function, if anything, we're trying to maximize something. We're trying to maximize some profit, and the values that correspond to the profit are listed in part A. The first ski is $40, so I'm going to put 40x, and then the next value is $60, which I'll correspond that to y. So again, that's all stated in part A. So they want us to maximize the profit. The profit is $40 for the first ski, $60 for the second one. Now we need the inequalities as well. And so that comes from the table. So I'm going to read each row one at a time. 9x plus 6y, it's something about 486. And then the next row, x plus y, and something to do with 63. Now the only question is, which inequality symbol do we use? Now it says the maximum labor hours. Maximum implies that our expression here, each expression cannot exceed, well, 486, cannot exceed 63. In other words, it has to be less than 486 or 63. But it can also be equal to. These are less than or equal to's here. So maximum implies less than or equal to. Because at the max, at the most, that expression can be 46 or 63. There is something else we're missing, though. There's technically two inequalities we're missing. What's that? They're non-negative, that's right, the non-negative restrictions. And you can go back and look at the previous examples. We always have this at the very tail end. And what this does is this says, well, x and y refer to number of skis. Number of skis that can't really be expressed as a negative number. So it's saying, well, let's acknowledge that we are not dealing with negative numbers of skis. So that's the first step. Notice our first step was just setting up the problem. Just setting up the problem as if it's a previous example. But from here, we can go about it about the same way. The second part, so what did we do after, or if we were given this? We graphed the inequalities. And now we're given absolutely nothing. So just nothing but white space. So we're pretty much in uncharted territory here. What I'm going to do, well, the first thing I want to do is I want to figure out the intercepts, all the intercepts. We have L1 and L2. And this will help me make the graph a little bit better refined. So we have L1 over here, 9x plus 6y, is less than or equal to 486. L2, I'll put that all the way over here. And I'll acknowledge that both of the lines are going to be solid because we have less than or equal to parts. So I'll skip that part and I'll just go ahead and find the x and the y-intercepts. Again, I have plenty of examples in previous examples for how to find the x and the y-intercept. We figure them out here right fast. The x-intercept is going to be 54. Y-intercept is 81. Do the same thing over here for L2. It's 81. The x-intercept and the y-intercept. Well, they're both going to be 63 here. Now, the reason why it's good to find the intercepts first is because this gives us an upper bound when we draw the graph. So what I mean by that is to go ahead and make some measly attempt at drawing an x and a y axis. Just something like that. Doesn't have to be great. Again, just like this. Doesn't have to be great. And the upper bounds of these graphs, I normally make the largest part of the graph the largest intercept. So I have a 54, an 81, and a 63. 81 is the largest number, so I'm just going to put 81. Because I know that any other intercept that we have is not going to exceed 81. So let's go ahead and plot these lines. X is 54. Again, don't have to be perfect with it. 54, right there. 81, of course, is going to be at the very top. And we can go ahead and draw a solid line connecting these. Now, your graph doesn't have to be perfect, but what it does need to do is provide perspective on when we go to plot the second line. Because for the second line, we have x is 63. We need to plot that point to where it's on the correct side of the previous point. So just as a reminder, this was x was 54. So for x is 63, obviously that needs to go on the right somewhere. And that's your main responsibility. You need to make sure you plot this. So this one's x is 63. So of course 63 is on the right. And then y is 63 for the y-intercept. That just needs to be below 81. And as long as you do that, get this intersection. If you plotted that second line incorrectly relative to the first line, you're going to get different points of intersection. And it's going to mess up your problem. You're going to misinterpret your graph. And since many of you don't have colors, then I would recommend putting L1 and L2 next to the first line you drew and next to the second line. Tell yourself, hey, this one's, this is which one's which. From here, we have 4 regions, and we need to figure out which one of the 4 we shape. So let's go ahead and start testing. Let's test 0, 0 for the first line. You plug in 0 for x, 0 for y. Get 0 is less than or equal to 486, which is a true statement. And since we get a true statement, this means we shade under the line L1. Oops, not L2, L1. L1. Which means we're not shading above L1. So X, X for those lines that we definitely do not shade. And what about the other line? To figure out which one it really comes down to. This one's true. Okay, so we test this. It does look like it is in fact true. Okay. So this is true. We shade under L2. So we don't shade above L2, or the second line, which means that we would exit out that one. And so it's this region in the bottom left here that we end up shading. So I'll go ahead and erase some of these details and clean this up. Let's go ahead and shade this in. And this is the region we shade. This bottom leftmost region. And so this tells us exactly which corner points we should consider. In fact, we have 4 corner points here. Origin is 1. That one's the easy one. We have this Y-intercept up here. We have this X-intercept down here. And we have this point of intersection here. Now again, one reason why it's good to label your lines is because when figuring out, say, this point, well, you could say to yourself, well, that point is the Y-intercept of the second line, which we already found over here. The Y-intercept of the second line was 63. That's 0, 63. And then similarly, or say this point down here. If we trace that line up, we see that that line is L1. So that's the X-intercept for the first line, which is 54. And then finally, there's this point of intersection for what seems to be L1 and L2. And so from here, again, point of intersection, we have to do a matrix. See, I should have some space down here. So this is for L1 and L2. Actually, I'm going to do this up above. I might need that space. Do it up here. So I'm going to scroll up just to remind myself which ones L1 and L2 are. 9, 6, 4, 86, 1, 1, 63. Do the RREF command. 1, 1, 0, 0. And we're going to get something out of this. Let's find out. Matrix, edit, 9, 6, 46, 1, 1, 63. We apply the RREF command as we did before. Matrix A. We get 36 and 27, which tells us the ordered pair for the missing corner points. So the missing corner point is 36 and 27. One, 2, 3, 4 corner points. So that's the information we derived from the graph. And so from here, so we just took care of that part. Now the final part is draw the table and ultimately determine the, let's see, was it minimum or maximum? It was maximized, so determine the maximum. So this is where that table comes into play. Again, we don't have a template for the table, so we're going to draw one. So the first column, corner points. And the corner points that we found, 0, 0, 0, 63, 54, 0, and 36, 27. So what are we plugging these points into? We're plugging these into the objective function, which we found in the very first step up here, 40x plus 60y. So we know exactly what to plug in. 0, 40, 54, 40, 36, plus, 60, 0, 60, 63, 0. The first one is 0, of course. 60 times 63, 40 times 54, 30 times 36, plus 60 times 27. 3,780, 2,160, 3,060. So those are the four. And so, since the region is bounded, the maximum exists. And so we can go ahead and conclude that the maximum is in fact the largest number in our table, 3,708, which is what we wanted to answer at the very beginning, 3,708, the very top. That is the maximum. And the maximum occurs when, this is just a fancy way of them asking for the ordered pair. 0, 63 is the corresponding ordered pair. So 0, 63. In order. Okay. So that is part A. The maximum profit is 3,780. The maximum occurs when 0 of the first ski and 63 of the second one are produced. Does anyone have any questions before we move on to part B? If not, part B is fairly similar. In fact, it's not a whole different problem. What it says is what happens to your maximum profit if you decrease the second ski to $55. So what that's ultimately saying is, all right, keep all of the inequalities, and with that, that means keep all the corner points. I'm going to reconstruct that part of the graph, the table here. So again, we're not changing the graph. We don't have to redraw a graph or anything. We're going to have a different table, the same corner points though, because we have the same inequalities. What we are changing is the objective function. Because what it's saying is, instead of 40x plus 60y, they're saying, what about if we decrease 60 to 55? Notice the slight difference in the objective function. And now it's 55y instead of 60y. And so this is what we need to proceed with. So basically, we're plugging in these ordered pairs into these new, this new equation. Now, 2 of these actually don't change. If you work it out, 2 of these do change. I should say 55 times 63. 40 times 36 plus 55 times 27. So the 0 and the 2,160, those actually end up not changing from before. If you work it out, you'll get those numbers anyways. So first one is 55 times 63. Then I'll do the last one, 40 times 36 plus 55 times 27. 3,465, 2,925. And so again, what's the maximum? Maximum is 3,465. Right, just go ahead and put 3,465. When does this occur? Well, it's the same ordered pair. 0 and then 63. So the ordered pair stays the same, but we get a new maximum. There is a part C for this problem as well, and it's the same kind of idea, except what about instead of decreasing from 60 to 55, what happens if you increase from 60 to 70? So it's the same type of problem. Again, one last time, write down the corner points. 0, 0, 0, 63, 54, 0, 36, 27. And the only difference is that we are increasing the second value to 70. So it's still 40x plus 70y. Notice the slight difference yet again in the objective function, plus 70y. These two are going to actually stay the same. If you plug them in, you'll see that for yourself. 40 times 0 plus 70 times 63, and then 40 times 36 plus 70 times 27. Times 63, 40 times 36 plus 70 times 27. 4,410, 3,330. And we see that we get a new maximum value, but the same ordered pair. $4,410, 0, and 63. And we are done with example 5. Does anyone have any questions before we proceed to example 6? If not, let's go ahead and move on to that example. Now, example 6, as you can see, there's this giant paragraph of all of these numbers. I'm not going to bother to read it. I'm mainly going to foreshadow what we are looking for. How many vehicles of each type did they rent to minimize the cost? So we're trying to minimize something. And then what is the minimum cost? So it's the same type of problem. It's just they give us even less information from the previous example. They don't even give us a table. Now, I gave a table that your homework does not give. So they don't give you this table. Maybe it helped me solve this, they might give you this table. But if anything, I'm giving you this as a template. Because we do need to ultimately convert all of these numbers to a table. And then from that table, we need to convert to the objective function and all of those inequalities. So I'm going to read all the numbers. I see the number 48. 48 corresponds to a bus and students. So if there's a bus, there's students, 48. All right, I see 5 chaperones for the bus. Bus, chaperones, 5. $1,400 to rent this thing. Well, what thing? The bus. So 1,400 goes down here. In this little table, this is something that you would normally have to construct on your own. I'm giving you this template, so that's just something to keep in mind. Okay, I see something about 8 students. 8 students corresponding to a van. 1 chaperone on this van. 1 chaperone on the van. How much does it cost for this van? $100. And then the number to accommodate seems to be the last column here. As I read on, there's 480 students. The officers must plan to accommodate at least 480 students. The reason why I underlined at least is because that will give us the inequality. At least means that our expression could be at the smallest 480, but it can be larger or greater than, in other words. So for the students, there is at least 480. For the chaperones, it says something about 55. Let me keep reading. At most, 55 chaperones. That gives us another inequality. At most 55, but it can also be less than 55. So this would be at most 55. So notice the inequality sign flips, which is going to give us an interesting effect on our graph, because they're not facing the same way. We'll see that momentarily. And so there's nothing really about rental cost. If we keep reading, we want to minimize the cost. Since we're minimizing the cost, that means that the rental cost is the objective function. Because that's what we're trying to minimize here. And so now we've taken that whole paragraph with all of these numbers, and we've put everything into a nice convenient table. So I'm going to go ahead and scroll past this paragraph here and go down to determining the objective function and the constraints. That is the system of linear inequalities. Now the objective function, well, first we need to figure out, are we maximizing or minimizing? It says the phrase minimize. It even says minimal. So we want to minimize the cost. And the rental cost gives us the values of 1,400. We'll append an X to it. And 100 for the van, which will append a Y to it. And if you want, you could put P equals to it. It doesn't matter. Mainly it's the numbers that matter. So that's the objective function. We're trying to minimize this objective function. And the linear inequalities will come from the two rows that we obtained up here. So we have 48x plus 8y is greater than or equal to 480. We have 5x plus 1y is less than or equal to 55. And naturally, we're missing something here. Non-negative restrictions as well. Which normally we take care of those inadvertently by just looking at the top right part of the graph. But we can list them here. So now we've taken the table and rewritten it as an objective function and a system of linear inequalities. So now we can scroll past the table, go down to this, and graph everything. So if anything, let's go ahead and graph the inequalities. We have two lines here, two non-trivial lines. I'll put the first line over here. 48x plus 8y is greater than or equal to 40. So the second line, also this line is solid. I'm not going to bother with that. Second line, 5x plus y is less than or equal to 55, which is also solid. Again, the equal to part. So let's go ahead and find the intercepts. Again, I'm going to breeze past the intercepts. X is 10, y is 60. And on the other side, x is 11, y is 55. And so I like to take the largest intercept and use that as the upper bound for my graph. Well, let's go ahead and draw a graph. It doesn't have to be anything crazy specific. All right, there we go. And so the upper bounds of this graph is going to be the largest intercept I see, which is 60. Put a 60 here, put a 60 here. And let's go ahead and graph this thing. For the first line, X-intercept of 10, put that over here. Y-intercept of 60, which of course goes up at the top. Go ahead and fill this in. All right, so, and I'll also put an L1 next to that line I just drew, so I don't forget about it. And so for the second line, we have an X-intercept of 11, which needs to go to the right of our first X-intercept of 10. I'm going to put that over here. This one's the X-intercept of 11. This one's the X-intercept of 10. So we need to make sure that they're on the correct sides of each other. And Y is 55. That's, of course, going to be less than 60. So we can go ahead and connect those two dots. And as we see, there are 4 regions here. One of these regions is a very tiny region in between L1 and L2, and the remaining regions should seem a little bit more, they should be a little bit clearer. So let's go ahead and test all of this. Go ahead and test 0, 0 to see where do we shade. We'll end up getting that 0 is greater than or equal to 480, which is false. It's a false statement. So we shade above L1. So we don't shade, of course, below L1. That tiny, tiny region between L1 and L2, that one's out. This region down here is also out. And we're left with 2 regions here. Let's figure out which one it has to be. Yet again, we test 0, 0. And so you would end up getting that 0 is less than or equal to 55, which is true. So we get some alternation here. So this is kind of interesting, which means we shade below L2. So we don't shade above L2. And so that means we shade this region right down here. So we shade that region. And from here, we can see that there are 3 corner points now. The point of intersection and these 2 X-intercepts. Those are the 3 corner points here. This first point over here is the X-intercept for what seems to be L1. The X-intercept of L1 was 10. It's 10, 0. The point to the right of it seems to be the X-intercept of the second line, which was 11. And then finally, we have the point of intersection for L1 and L2, which, as you would imagine, this evokes a matrix. Matrix is between the 2 lines. So the augmented matrix is 48, 8, 480, 5, 1, and 55. So let's go ahead and figure that out right fast. 48, 8, 480, 5, 1, 55. And we apply the RREF command once more. Get 5 and 30. So this column tells us that the missing point is 5, 30. And so we have 3 corner points here. 5, 30, 10, 0, and 11, 0. And so that's the information we derive from the graph. Now that we have the corner points, we can go ahead and generate the table. It involves the corner points, which there's only 3 of them, so a little bit less computation. 10, 0, 11, 0, 5, 30. Now the objective function, we remind ourselves, we found this in the very beginning. It's that function we want to minimize, a 1400x plus 100y. 1400x plus 100y. And so now we know exactly what to plug everything into. One, 4, 0, 0, 0. Well, 5 plus 100 times 30. Okay. And this to 0. There we go. This is 15,400 and 10,000. So from here, to minimize the cost, we need to find the smallest, which is 10,000. But they are first asking for, not the minimum itself, they first want the ordered pair, which would be the 5 and the 30. Notice they're kind of switching the order. And then they want the minimum, which would be the 10,000. And that concludes this example. Does anyone have any questions before we look at the last example for Math 105? So if not, let's go ahead and knock this last one out. Okay, so good news, they gave us a table, so hopefully that will expedite this process a little bit. So as I read the paragraph, I always want to take a look at any numbers that I see. And I do see some numbers. Not only do I see 2,800, I see at least 2,800, which gives us an idea about an inequality. Now, what is that 2,800 referring to? Of course, referring to pounds. I don't see, well, I see phosphoric acid. And so there's actually a row for phosphoric acid. So I know for that row, well, at least means that at the smallest, it's 2,800, but it could be larger. So at least 2,800 for that second row. Because that 2,800 refers to phosphoric acid, and I see that phosphoric acid is the second row. As I keep reading, I see at most 400 pounds of chloride. Well, here's chloride, it's the third row. At most means that we have a less than or equal to sign, and 400 is the Well, this maximum for the chloride. So why did we skip the first row? I don't see anything for nitrogen. Well, let's just skip it for now. So that's everything I got from the paragraph above. Now, when I start reading part A, if the grower wants to maximize the amount of nitrogen, aha, there we go. Maximize nitrogen. Nitrogen immediately becomes the objective function. That's why. So we want to maximize nitrogen. And so nitrogen has a 2 and a 3. So that would be 2x plus 3y for its row. So nitrogen has the 2 and the 3, so 2, I'll correspond that to x, 3, y. And so the inequalities here, I think those should be clear, especially with the symbols that I have outside of the table here. 8x plus 8y is greater than or equal to 2800, and 2x plus y is less than or equal to 400. But of course, there's something missing here. We need the non-negative restrictions as well, which basically says just look at the top right part of the graph, which is something we're always doing in this section. So we have the objective function, we have the inequalities. Let's go ahead and draw the graph. So I'll scroll past all of the table stuff. I'll only focus on the objective function and the constraints. I'm yet again going to denote these as L1 and L2. Do the same thing as before. Here's the first one, which of course is solid line. And the second one, which is also a solid line. So let's go ahead and find the intercepts. Seems like in both examples, we get 350. 2800 divided by 8, I believe that is in fact 350. The second line, it seems like we get x is 200, y is 400. So now that we have the intercepts, we can go ahead and figure out, well, we can draw this thing. Okay, I'll draw that. And I know that the upper bounds, or I'll make the upper bounds the largest intercept, which is 400. Well, let's go ahead and plot the line. 350, kind of close to 400. 350, kind of close to 400. In fact, just foreshadowing here, give a little bit more space. Let's do that. And we can go ahead and connect those two dots. And put a little label of L1 next to it. Second one, the x value is 200, which is of course less than the 350 that we have plotted on the x-axis. 200 about right here, and 400 obviously is going to go on the top. And that'll be L2, the second line. Now we have 4 regions, and we need to figure out, of course, as we've done before, which region do we shade? So let's test 0, 0 for the first line, which we will end up getting that 0 is greater than or equal to 2800. which is, of course, false. So we shade above L1. So we don't shade below L1, so those two regions are out. The second one, we get that 0 is less than or equal to 400, which is true. So they alternate. We shade below L2. Means we are left with this tiny region up top here. I don't know if it's hard to see. Hopefully the X's in the other regions make the shaded region a little bit more visible here. But that evokes 3 corner points. Point of intersection is 1, this Y-intercept is 1, and this Y-intercept is 1, which I filled in black to distinguish them from everything else going on. Okay, so the first corner point, I'll find the one next to L1. So that's the Y-intercept of L1, which is 350. The next one is the Y-intercept of L2, which is 400. And then finally, we have the point of intersection for L1 and L2, which again needs a matrix. So I'll do the matrix down here. It's going to be a matrix between the 2 lines up top in our system, which is 8, 8, 2800, 2, 1, 400. Because we're running a little bit low on time. I believe this is 50 and 300. Someone already figured this out?
Mm-hmm.
All right, 50 and 300, cool. And so that tells us exactly what this final point is. So we have 3 points of intersection. 1, 2, and 3. So from here, we can go ahead and put those on a table, just like we did before, and compare them with, or plug them into the objective function. So let's go ahead and list out the corner points that we found. One was 0, 350, one was 0, 500, and one was 50, 300. Just verify that that was right. Good, good, and good. The objective function as well that we found that at the very beginning, 2x plus 3y. Two times 0 plus 3 times 350. 2 times 0 plus 3 times 400. 2 times 50 plus 3 times 300. And so, good thing these are easy calculations to do. And 900, that's 1,000, I believe. 50, 100, 900, 1,000. So with this table, well, the good news is part A wants the max, part B wants the minimum. So we don't have to really do anything else here. Just a bunch of observations. So for the maximum that in part A that they first want, well, the region was bounded, so we know that this does in fact exist. And so the maximum is in fact 1,200 with the ordered pair 0, 400. We'd want 0, 400, the ordered pair first, and then what the minimum actually is, second. It's normally characterized by 2 blinks and then 1 for the following one. And then part B just wants to minimize this instead, which means we do no extra work. We just find the smallest value, which is 1,000, with the corresponding ordered pair of 50, 300 to get 1,000 as the minimum. And that, my friends, concludes Math 105.